So what we need to look at now is looking at how wavelengths, again, we already saw the formula using the Planck's constant and Planck's theory, and also the speed of light, but that visible light spectrum. So again, if we look at my spectrum here, we've got Roy G Biv, and again, the wavelength. These wavelengths, again, are increasing as you go from violet to red, so kind of decreasing when you go to Roy G Biv. But the red wavelength is, the violet wavelength is right around 400 nanometers. Okay, nanometers. Remember, a nanometer is times 10 to the -9 of a meter. And in general, we can go by about 50, so that would be 455, 556, 657, and it could be a little bit more than 700 nanometers for red, but basically that's about what the wavelengths are in, of course, nanometers. I didn't write it all, but there you are. So if you're given a specific color of a wave, you see the expression of color, then you can determine what the energy is just from what color it is. Just from what color it is. I wouldn't have to give you any values at all, because if you know the color, that color can correspond to a wavelength. That wavelength can be then converted to frequency and then the energy. And again, what I'm talking about here are your speed of light formula and your Planck's theory formula. Okay, so using those two. So let's think about it. If I say we have a red orange light, L-I-G-H-T, okay, and I don't give you anything at all in terms of what the wavelength is or any values, I can say, what's the energy associated with that red? You see, take a look at it, it's red orange. Or I could have said blue and violet, blue and green, so a little blue-green color. Well, let's say that a red orange is 675 nanometers. So that's what the wavelength would be. So that's really what's kind of given. The wavelength is given. Now, I want to use this formula first, and then this formula second in terms of solving for my energy, because that's what I really want. I'd love to use this one first and just be done with it, but because I don't have the frequency, I have the wavelength, then I got to solve for frequency first and then solve. So let's go ahead and do that. I'm going to take this formula down, and I'm a big fan here of rewriting it. Here's my formula. I'm going to rewrite it, which is going to be the C over the wavelength. Frequency is going to be 3.00 times 10 to the 8th meters per second over. Now, I can't just use 675. I can't, because it's in nanometers and my speed of light is in meters per second. So since it's in nanometers, I need to change that to meters because my speed of light is in meters. Let me show you how we're going to do that. Nanometers 675. Actually, let me give you a different color here. I think the yellow will be a little bit better. 675 nanometers, and I want to solve how many meters that is. Well, the way we look at that, nanometers is times 10 to the -9, meters is 10 to the 0. That's a 9-place move. This is smaller than this. We're moving this way, right? The smaller thing eats the bigger thing. So we're moving to the left 9 places. 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, if you want to write down here in the bottom, if you want to write 0.000, you can do that. I'd rather write it in scientific notation. So in order to write in scientific notation, here's my decimal right here. I'm going to now go 1, 2, 3, 4, 5, 6, 7. Notice that when I come back to write it as 6.75, right, times 10 to the -7 meters. I've gone 9 places this way, but it was at 675. So I went 1, 2, and then 7 more. That gives me 9. But now I'm coming back and I'm stopping right here. So nanometers to meters, you're going to get 6.75 times 10 to the negative 7 meters. Since all our colors are between 400 and 700, then you should be able to understand that if I had a green one, 550 nanometers, that would be 5.50 times 10 to the negative 7 meters. Why? Because nanometers to meters is 9, but I'm writing negative 7 because I went 1, 2 extras before I came back to here. All right? There's a whole mess right there, but let me go right ahead and solve this formula right here and then keep going. So actually, let me go ahead and write my formula again. I rewrote it, which was C over the wavelength. Okay, so let's do this, and let's take my calculator. 3.00 EE8 divided by 6.75 EE negative 7. I get a, I think I'm writing here. I get a frequency of 4.44 times 10 to the 14th 1 over S. I'm going to take this formula down. E is equal to 6.6262 times 10 to the negative 34th time. I really like writing my labels. I really should. Joules seconds times your frequency, which is right here. I'm not going to go ahead and write it again. I'm running out of room. So times 6.6262 EE negative 34th. Solve it. The energy associated with a red-orange light is 2.94 times 10 to the negative 19th joules. And there would be my answer. It's a lot of work on there, a lot of kind of crossing out and stuff, but that's how we would use that.